forgot to turn on the air conditioning. They think that winter in Brazil does not need air conditioning. But mosquitoes comes, right? They don't know winter, seems like. Okay, so we are ready. We're going to give you we have the first plenary talk. It will be given by Professor Sánchez-Soto. He is a superposition of Spain and Korea, German. And he agreed to give you the opening. Before he gives his talk, I would like to ask your excuse to present a little video of Luis Davidovich, which is the chair with me of the conference. But Luis got a health problem. And then he was kind enough to put a 2 minutes video. So if you let me, Soto, I need the help to put in here. He just want to give you the welcome. He just got out of the hospital. And then immediately after, we started the conference of Professor Sanchez, which is Quantum Light, Coherent Photon Statistic and Phase Space. Wow, that's a very nice name. Okay.
Hello, I'm Luis Davidovich, co-chair of this conference together with Vanderlei Bagnato. I wish you all an excellent conference. I'm quite sure it will be successful in view of the bright people who are participating in it. I'm sad I cannot participate in this meeting due to health problems just prior to this meeting, but I'm recovering fast, and I look forward to participating in the next Laser Physics conference and meet you all. You know, being a co-chair of a conference together with Vanderlei Bagnato is very comfortable because he does by far most of the work. So thank you, Vanderlei, for your good work, for the work of you and your group towards organizing this conference. And I really look forward to meeting you all in the next Laser Physics conference. Welcome to Brazil. Welcome to Laser Physics 2024. See you soon. Bye-bye.
So, good morning, everybody. Thank you for being here. I start by thanking the organizers, and especially Vanderlei, for bringing me here. He was mentioning that coming from Europe is a difficult trip. I'm coming from Korea. It's even more difficult to come here, but it's worth trying, okay? So, I'm not a laser physicist. I'm not talking about laser. I'm just a fundamental physicist, just trying to understand the basics of the interaction of light with matter. And so, as a pure quantum guy, I live, as Vanderlei was mentioning, in a linear superposition. I'm living in a delocalized state between Madrid, okay, and a tiny place in the south of Germany, Erlangen, where there is a Max Planck Institute for the Science of Light, and my other co-author, Gerd Loix, is the former director of the institute. So Erlangen is a very, very tiny place, I mean, few kilometers away from Nuremberg, from those that you don't know, and it's famous for three things mainly, okay? One is, if you are a mathematician, there is something that is called the Erlangen program. Okay, so Felix Klein was a professor of mathematics there, and when he took the first lecture in his chair, he was, asking for a future program of research. The second thing is that it's the central headquarters of the largest German company, Siemens. And the third one for young people is even more important, is the place where MP3 was invented. So everybody is talking about MP3 because it's linked to Erlangen. So the idea I want to talk, I'm sorry for the resolution because the Mac is not working. Okay. So I'm just giving three main topics that are all of them related to the idea of the vacuum. So traditionally, in the classical physics, since Aristotle, we have two basic principles about nature. The first one is natura non fexit saltus. The nature never makes jumps. Everything must be continuous. And the second one is horror vacui, the fear of the vacuum. So I will try to convince you that we should change the idea from horror vacui to gaudium vacui, so the happiness for the vacuum. So since this horror vacui, this fear of the vacuum, people was assuming that what was in vacuum was something that along the years was known as the ether. The ether was introduced by the Greeks and was through all the centuries in physics until probably Albert Einstein was the guy who really said no more ether in the realm of physics, although if you read carefully, the relation of Einstein with the ether was changing in his life. So we know now that the vacuum is not void, it's a dynamical quantity, and as a dynamical quantity introduces many physical observable effects. And I want to talk precisely about three of them. When you change, for example, the boundary condition of the vacuum, you get the famous Casimir force. The modern vacuum is a kind of ether, or Frank Wilczek says, is the greed of everything happens in our universe. So the only difference with the classical ether is that it's Lorentz invariance. The vacuum is full of virtual particles, but for my talk, I want to put three topics I want to deal with. First of all, the vacuum is responsible for something that is called the spontaneous emission. So the spontaneous emission is responsible for, if you are a laser physicist, for noise, but also is responsible for the lamp shift, for the width of the spectral lines. So the spontaneous emission is something that we want to look at with much more care. Second, we'll see that also the vacuum is responsible, the properties of the vacuum are responsible for the properties of the light in the medium, in particular for the velocity of light and also for the strength of the interaction between fields and particles. This is the fine structure constant. And finally, we'll see that for the quantum vacuum, we cannot define its properties in terms of intensity correlation, and I will come to that in a minute. So, if the vacuum is kind of ether, has to have the properties of kind of dielectric. So remember, in electricity 101, we have this traditional way of introducing the electric field in the matter and the magnetic field in the matter. So it's rightly defined in terms of epsilon naught and mu naught. Well, a typical reaction is, epsilon naught and mu naught are not interesting quantities, are just constants that are adapted to the unit system. This is typical. So, no, who cares? And the answer is no, it's not. Because you can say, oh, I like Gaussian units, and in Gaussian units there is a 1 or a 4. There is a 4 pi or a 1. So what? Irrespective of the units you choose, epsilon naught, mu naught, 1, the question is that these properties here define the velocity of light in vacuum. So this means there is physical content in this way. So there are two, to appreciate that this epsilon naught and mu naught are not so well understood sometimes, I have two quotes, one from a very, very famous book by Igor Tamm, Nobel Prize, who says explicitly that the electric displacement, D, is made of the sum of two absolutely different physical quantities. One is what he calls the field intensity, and the other one is the polarization induced in the matter by external fields. So one can say, so this is completely different from that other. This is the other citation is by, oh my God, is by Ed Purcell, also Nobel Prize, in his famous, probably some of you remember this famous Berkeley physics course, 5 volumes that for Physics 101, okay? And in the second volume, he writes that the vector D is an artifice, and then is not at all helpful, and explicitly say the problem began with Maxwell, and the student is sure to encounter it in another books, many of which treat it with more respect than it deserves. So I fully disagree with both. I think these two guys are really representing the response of the matter, usually a linear response, but also, and these two guys are just the linear response of the vacuum. I will try to interpret this in a moment. So if now you go to any textbook of quantum electrodynamics, of quantum field theory, don't worry about the calculations, I will skip all of them. So you see this typical diagram, Feynman diagram, that is called the vacuum polarization. So this is the physical idea, is the first diagram any student in quantum field theory has to renormalize. It's the first one. So the basic idea is you have a photon here running, stars here, and then out of the blue, two virtual particles, electron and positron, are created. Because they are virtual, they can exist only because of the uncertainty principle a very short time, and they annihilate, and then the photon continues. So when you try to apply typical Feynman diagrammatic, you immediately recognize that this vector, this diagram, is divergent. Why? Because in principle, the momenta of this electron and positron can be arbitrarily large. And this originates the typical divergence that was a nightmare for Dyson, Feynman. The question is that if you go, for example, to the modern view of quantum field theory, Peskin, Schroeder, you have like 20 pages of lengthy calculations, and you don't know anything what he's doing. Let's try to, yes, think about, and the other thing he's doing is that when you have this kind of virtual particles, you have a kind of virtual dipole. And then the vacuum gets polarized. If you remember when you are teaching to the students and you say, oh, epsilon naught is the vacuum permittivity. So this means the vacuum is polarized and behaves as a real dielectric. The question is, you reinterpret that, and then after these long calculations, you get epsilon naught, which is what we know as normal epsilon naught, plus this correction that has this horrible expression here. Forget about the expression. The question is, this guy depends on k squared, and k is just the quadrivector of the photon. So when this is, remember from relativity, this is the trivector, this is omega. So for a photon on shell, purely propaganda vacuum, this is 0. The photon is generate time. So and this is 0, and we get epsilon naught. But in principle, we have this guy here that has a logarithmic divergence. So notice that this is only for photons, and I wrote that for electron, positron, but I could write that for any kind of elementary particle. So in principle, this diagram should be sum over all the leptons that can contribute, so muons, everything. So this means that what is boiling down in the vacuum is a dance of all the elementary particles in the universe. Good. So if this guy depends on k, this means this guy depends on the energy. And sometimes people say, well, this fine structure constant that is usually defined as 1/4 pi hc epsilon naught over e squared of epsilon naught, if this guy runs, this means that the charge you see is renormalized. This is the famous charge renormalization. So this means alpha means just what is the strength of the interaction of light and matter. And this strength goes to 0. So, I mean, the inverse goes to 0, so the strength goes to. Okay, so if you look at this expression, what is the previous one, okay? Forget about the complexity, it's just the previous one. This is P naught, P2. Then, you know, this guy goes to decreases. One can think that there are a regime of energy in which this guy goes to 0. This is something that in quantum electrodynamics is called the Landau pole. This is the energy in which all the interactions are the same, and they are so screened that the interaction is infinite. So if this Landau pole exists, I mean, this is the position of this guy, and then if this is 0, I can really make this equation, solve this equation, and I get that alpha minus 1, which is essentially epsilon naught, is this guy. And this means that I have a closed expression for alpha, for the fine structure constant, or if you prefer, for epsilon naught. So this is the first calculation ab initio of a constant that usually is assumed to be given by the system of units. So that was already started by Vicky Weisskopf and Kurt Gottfried in his book, but I think I will skip this and go to this, okay? So now we can think in a very simple model. We know then that according to quantum field theory, what we have are just these virtual pairs, virtual, but then they are short-lived. So this means that you have a electron, positron, electron, positron, and then you can think, okay, they are produced, they separate. Can, in a way, an electron and positron get a bound state? This was something that was considered by Wheeler, and he called that the positronium. I mean, the parapositronium, because the spin is 0. So this means these guys are creating, like virtual dipoles. So this idea was explored by Oppenheimer, by Dickey, by Wheeler, by Feynman, trying to understand what is going on the vacuum. And if you think in what is the separation typical that you can assume between these two guys, so what is the distance? I mean, we need to put some numbers, okay? Imagine I put just the Compton wavelength. What else? And then I assume that these two guys are like linked by a harmonic oscillator force. Which is the strength of this harmonic oscillator? Twice the mass of each of the particles. Then this is a classical problem in physics of dielectrics. What is the polarization generated by those states? And I can calculate that, so I put that for my students as an exam. And the final result is this. Just epsilon naught is 1 over hc, sum over the square of the charges of all the particles, elementary particles, and probably some factor f that takes into account that this is a crude approximation. That's a factor. So the final result is that epsilon naught is just giving us an indication of how many elementary particles are in the universe. So if I take the value, epsilon naught, I need to assume what is the value of f, which is a kind of factor. If I take f equal 1, I get that there are 48 elementary particles in the world. But, I mean, if I remember, I have before an expression for the epsilon naught. So I can use this expression of the epsilon naught, and then I can try to compare with this factor. So this means that this factor is related to the Landau pole, in a way. So let me try to just imagine that I take the number of particles in the standard model, and I take the Landau pole at the Planck energy, then this factor is 0.74. Yeah, incidentally, some years ago, Seldovich did some similar calculations, now involving gravity. And he got this formula for, this is essentially the renormalized charge, so this is essentially for epsilon naught. And he writes that to agree with the experiment, the number of types of charged particles in the universe must be 13. So the message to take home is that epsilon naught is not a trivial constant. It's just giving us an indication of the fundamental nature of the physical laws. So with this, I pass to the second topic. It's about spontaneous emission. So I'm interested in this spontaneous emission can be typically understood as stimulated emission stimulated by the quantum vacuum fluctuations, okay? So let's imagine that I have a single atom. How can one achieve strong coupling with the radiation? Well, the traditional way is to put the single atom in a cavity. This, of Of course, adjusting frequencies and all that means that you can go to all these famous guys who were able to go to the strong coupling in this limit. And one question is, do you think that we can have a single atom in free space and have a lot of coupling? And the answer is obviously not. But let's think carefully. I mean, imagine that instead of illuminating the atom with a normal plane wave, I illuminate the atom with a dipole wave, which is just the reverse of that. So in this way, this coupling can be very high. So this was proposed in '86, and that triggered a project in Erlangen that is the project is 4-pi pack. So 4-pi from solid angle photon-atom coupling. So the project is 10 years of really, really heavy experiments, and the first results are now cooking. So what is the idea? The idea is to have a single atom in free space. So we prepare a parabolic mirror. White aperture is 4-pi, solid angle, and the parabolic trap was designed by Dave Wineland when he still was at NIST. So there is aluminum, then there is an electrode, and we trap there a ytterbium ion. And so we want to, I mean, a single atom is just a single classically dipole. And a dipole emits a dipolar wave. So the idea is, if this is a linear dipole, then we got 94% of coupling between the field and the atom in free space. Just because, remember, the parabolic mirror, any light in the focus goes to infinity. So moreover, we tailor everything such a way that we produce radial polarization at the input in such a way that the polarization is completely parallel to the atom at the focus. Okay, Lorenzo. So now, remember, we are now interested in considering the spontaneous emission out of this single ion. The advantage of being in the focus of a parabolic mirror is that instead of going the spontaneous emission in arbitrary directions, the parabola is focusing in the directions we go. And now the question is, okay, we know that in spontaneous emission, the atom emits a single photon wave packet that has approximately an exponential shape. This is the famous Weisskopf-Wigner theory. So, can we make spontaneous emission reversible? Can we? The answer is yes. Why? The argument is very simple. The physics, I'm not an experimentalist, so don't ask me many details, but the idea is, look, if this is the atom, so the atom emits a exponentially decaying factor. If you really want to have things reversible, you need to illuminate the atom with the exponentially rising pulse. It's not just the mirror image of that. So we did that, and we were able to make the atom coupled with spontaneous emission, 90%. Now the question is, okay, so this is in principle, the citation probability is 100%. We manage in the lab only 90%. Final question. So if you have spontaneous emission, we know from decay that when you have spontaneous emission in a set of atoms, this can be really spatially coherent. This is super radiance. But if I ask any of you, what are the coherence property of spontaneous emission? Spontaneous emission is caused by random fluctuations of the vacuum, so I don't expect to have coherence in spontaneous emission. That was our original ansatz. So we decided to do the experiment. The experiment, so this is still preliminary. The experiment took 5 years, really 5 years, okay? It was far from simple. The idea is simple, so we have the trap, okay? So the trap, we have this being splitters, and we send here to this photomultiplier at 297 nanometers, which is the resonance of the emission of the line we are interested. Then we sent the light through this intensified single photon MCCD camera. So we get the picture of the atom here. And after that, we sent the light from spontaneous emission to this interferometer. We can control. And then the question is, in these photomultipliers, we can calculate the visibility of the potential interference of a single photon from spontaneous emission self-interfering with himself. So the results are from last week. So first of all, we measured G2, and there is clear evidence that we are in a single photon case. But we also measured the visibility of these two arms of the interferometer, and we get 70% of visibility. So this means spontaneous emission of a single atom is spatially coherent. So, last topic. How much time? 10 minutes? Okay, good, I will finish. So, we measured G2. We are dealing with single atoms. So G2, I mean, these correlation functions, I mean, I put G2 in 0, but I can put G2 in tau, G4. These correlation functions are at the realm of of discrete variables. You detect clicks, and then correlation between clicks gives you all the physics. But G2 is not giving anything about the atom, about the vacuum. However, we have another approach. It's continuous variables, okay? In which everything is described in phase space. This is a single mode, X and P. And then in phase space, you can define something like our quasi-distributions. I mean, this is the Wigner function. But in principle, you can define a complete set of quasi-distributions that mathematically are nothing more than the symbols of the density operator. The question is, I mean, these two communities live far away. People who is making photon statistics, they don't want to know anything about Wigner function. And people that is doing Wigner function, they say, I mean, what's the need to do any click? And the question is, this guy contains the whole information about the system. And this guy, the hierarchy of this, contains the whole information. How can one cross-talk these two fields? And the answer is also simple. Well, first of all, these are the typical correlation functions for a coherent state. One, coherent state is always coherent. A thermal state, coherence 2. And a squeeze state that, as we see, is 3, 1 over n. So we have this typical 1, 2, 3 dimensions that Wolfgang Schleich, that is not here yet, right, was so interested years ago. So, what is the way we try to link both descriptions? Okay? If you rewrite this G2 in terms not of the average number of photons, but in terms of using symmetrical order, so Weyl order, then the average number of photons can be calculated just using the Wigner function. So this means that using Wigner function, you can calculate G2, or knowing G2, you can reconstruct Wigner function, at least for a Gaussian state. Now, is that working? So we decided to go for a recent experiment that was done in École Normale in Paris by the group of Julien Lorat. So we have, sorry for that, we have an OPO. So in this guy, we produce typical entangled states, entangled polarization entangled, okay? So in one part of this light comes this way, and we use a local oscillator for a homodyne detection. And in this other photon goes, these two photons originated here. We have a polarizing beam splitter. One goes here, the other goes there. So we can control here, measuring the G2, and here we can make homodyne detection. And then we can reconstruct Wigner function. So we can do simultaneously live in continuous variables and discrete variables. Moreover, we put here a halfway plate. Since these guys are entangled in polarization, if the halfway plate is at 0, we have one EPR state, I mean completely entangled state. But if we change the angle of, you can move to individual squeeze states, we can move to any kind of states. So first of all, this is the reconstructed Wigner functions for several angles of this halfway plate. We see the shape of the Wigner function is changing, and from this we can calculate the variances in position and momentum of this state. And we also measure G2. So these are the results using direct detection, measuring G2. These are the results using homodyne detection. You can say they don't look so good. They don't. Why? And the reason is physically is simple. I mean, G2 is well known by people in discrete variables, is invariant under losses, but the Wigner function not. So even if you try to correct as much as possible losses, the losses affect a lot the reconstruction of the homodyne detection, but not G2. But in any way, this is a way to show that in phase space you can accommodate discrete variables and vice versa. And with that, thank you very much for your attention. Absolutely.
With the permission of the speaker, he will accept all the questions in the world in the coffee that's served. So please go, and let's come back in 20 minutes so we can be only 10 minutes late for your lunch. Thank you. Enjoy. Coffee. Coffee can get cold. Rush. Come back, don't worry, don't forget to come back.